Hi, this is my presentation on using big data software along with healthcare data. This presentation was generated for the Big Data Analytics for Healthcare final project at the Georgia Institute of Technology. Let's begin. Technology's use and impact in our daily lives continues to grow, from emails, texts, and blogs to music, images, and videos. More and more content is generated every minute of every day across the world, resulting in more and more data. The term most often associated with this ever-increasing data is big data. One definition of big data is data that exceeds the processing capacity of traditional database systems. The data is too big, moves too fast, or doesn't fit in the structures of traditional database architecture. To gain value from this data, you must choose an alternative way to process it. Healthcare data is one of the many growing areas dealing with the massive influx of data. From wearable health devices to more technologically advanced medical devices to increasing access to healthcare, the number of areas where data is generated and quantity of data generated is continuously growing. ACHILLES is an acronym for Automated Characterization of Health Information at Large-Scale Longitudinal Evidence Systems. It is an open-source software tool that is designed to provide analytics for healthcare data. The tool runs over 150 various analytics against the database to produce the various characterizations of the data. For the author, with a relatively small 3 GB dataset, this process took in excess of 30 minutes to completely run once. Big data software's key selling point is the faster processing of data. Therefore, this project's objective is to demonstrate the power of big data software in processing large healthcare datasets over the use of traditional relational databases. This project consists of two phases. On the left is the ACHILLES stack. ACHILLES is written in the R language and queries data from a traditional relational database. In the case of this project, Postgres. This first phase of the project consists of benchmarking ACHILLES analytics and then identifying long-running portions of ACHILLES. On the right are the big data tools used for this project. They consist of Amazon Web Services Big Data Platform, called EMR, a small Scala-based program, and Apache Spark. The key tool is Apache Spark. It is an in-memory large-scale data processing engine. The tool is well known for its lightning-fast cluster computing. The Spark benchmarks were done with a single node and a 4-node cluster to also understand the scaling aspects of Apache Spark. Phase 2 consists of taking the selected long-running analytics from Phase 1 and running them using Apache Spark. Phase 1 started with benchmarking every analytic ACHILLES executed. This graph represents the clock time for each analytic. The author discovered how the vast majority of analytics took less than 1 millisecond, and it was only a handful of analytics that were resulting in long clock times. Drilling down even further, the ACHILLES benchmarks were broken down into individual analytics by group. Group 300 and 400 were eventually chosen as targets for Apache Spark. Group 400 was due to the fact that it is the overall longest running group. Group 300, while only containing 3 analytics, each takes a considerable amount of time to run. Time per analytic spent, Group 300 was nearly the largest when compared to all the other groups. Therefore, analytics in these two groups were then written for Apache Spark. The results for Group 300 were very favorable for Apache Spark. Overall, 30 seconds of time were saved compared to Postgres. The 4-node cluster did take slightly longer, only a few milliseconds, than the single node. This was due to the time required to distribute and pull everything back together from the cluster. The first 3 Group 400 analytics, however, resulted in poor results as both Spark environments were unable to even come close to the Postgres results. This was due to the very costly operation of a group by in Spark. However, the 4-node cluster showed nearly a 4x performance improvement over the single node environment. The author believes if additional nodes or even more data were considered, the Spark 4-node cluster would continue to have improved and eventually done better than the Postgres environment. Finally, the last four Group 400 analytics showed the sheer scaled speed of Spark. The Postgres environment took 50 seconds to run all four analytics. The single node took 10 seconds, and the four-node Spark environment took only a single second to complete all analytics. The distributed and in-memory advantage really shined with these analytics. In conclusion, Spark, especially as seen in the last example, can be blazingly fast. Computation that takes advantage of speed of in-memory computing results in massive time savings. In this project, additional nodes helped process the data even faster. A future research project could include looking at how additional nodes could have helped even more, for how long, and to what extent. With the increasing quantities of data in the world, Spark is well suited and well positioned for processing big data. Whether the data are health data, as seen here, financial data, high-performance computations, or other types, Spark is definitely one data processing solution to consider. Thank you for watching.